I'm going to tell you about one of the craziest ideas I ever heard in physics. And the remarkable thing is, it came from one of the smartest people I ever knew, John Wheeler. This was back in 1940, when I was a graduate student at Princeton, and I got this telephone call. Wheeler calls me up and he says, "Feynman, I know why all electrons have the same charge and the same mass." Well, that's an interesting question, right? I mean, you look around at all the electrons in the universe and they're all identical. Exactly the same charge, exactly the same mass, exactly the same everything. Why is that? You'd think if you're making electrons, maybe you'd make them a little different, like people. But no, every single one is precisely identical. So I say to him, why? And he says, because they are all the same electron. Now, when someone tells you something like that, you have to stop and think. What does he mean they're all the same electron? There are billions and billions of electrons just in this room, in your body, in everything around you. How could they all be the same one? Let me explain what Wheeler was thinking. You see, in physics, we have this way of representing particles moving through space and time. We draw what we call world lines. Picture this. You have a graph with space going one way and time going the other way. An electron sitting still would just be a line going straight up in time, right? If it moves, the line tilts a bit. Every particle traces out its own line through space-time as it moves around. Now here's Wheeler's wild idea. He said, what if all those lines aren't separate? What if they're all part of one gigantic, tangled, knotted up line, all traced out by a single electron? Think of it like a piece of string that's been tangled into this enormous knot, going back and forth, up and down through time. Now imagine you take a slice through this knot at one particular moment in time. Your knife would cut through the string many, many times. Each place where you cut represents an electron at that moment. That's why we see so many electrons. They're all just different places where this one electron's world line crosses through our particular moment in time. But here's where it gets really interesting. If this electron is zigzagging back and forth in time, then some parts of its path must be going forward in time, and other parts must be going backward in time. And Wheeler says when an electron travels backward in time, we see it as a positron. Now, you might not know what a positron is. It's the antiparticle of the electron. It has exactly the same mass as an electron, exactly the same properties, except its charge is positive instead of negative. We discovered positrons in cosmic rays in the early 1930s, and they show up when you smash particles together at high energies. When an electron and a positron meet, they annihilate each other and produce light. So Wheeler's idea is that a positron is just an electron running backward through time. Think about that. What does it mean for a particle to go backward in time? Well, imagine you're watching a movie of an electron. It's got a negative charge, and it's moving, let's say, from left to right. Now, you run the movie backward. What do you see? You see what looks like a particle with a negative charge moving from right to left. But from the perspective of the reverse time, it's like watching a positive particle moving forward. The mathematics works out such that an electron going backward in time looks exactly like a positron going forward in time. Now, I have to be honest with you. When Wheeler told me this, I thought it was crazy. I mean, really crazy. But there was something about it that caught my attention. The idea that you could represent a positron as an electron traveling backward in time, that part was interesting. I didn't take seriously the notion that all electrons were literally the same electron, but this business about positrons being backward in time electrons, that I stole. Let me tell you why I thought Wheeler's idea couldn't be right, even though parts of it were useful. If all positrons are just the same electron going backward in time, and all electrons are the same electron going forward in time, then there should be exactly the same number of positrons as electrons in the universe, right? Every time the electron reverses direction, you get one of each. But when we look at the universe, what do we see? Lots and lots of electrons, and very few positrons. Matter dominates over antimatter. There's way more stuff made of electrons than positrons. The numbers don't match up. So I said to Wheeler, but John, there are far more electrons than positrons in the universe. Your theory doesn't work. And you know what he said? He said, well, maybe the missing positrons are hidden in the protons or something. Now, that's not a very good answer. I mean, you can't just hide missing particles inside other particles to make your theory work. But Wheeler was such a brilliant guy, he could get away with saying things like that. He was thinking out loud, exploring ideas, seeing where they led. That's what good physicists do. The The real value of Wheeler's idea wasn't that it was literally true, it was that it got us thinking about time and particles in a new way. See, in the equations of physics, there's a beautiful symmetry between past and future. The laws work the same way whether you're going forward or backward in time. An electron moving forward in time really does look mathematically identical to a positron moving forward in time, or equivalently, an electron moving backward. I took this idea and I used it. In 1949, I published a paper called The Theory of Positrons, where I showed how you could reformulate quantum mechanics using this notion of particles going backward in time. Instead of thinking about empty space being filled with a sea of negative energy electrons like Dirac had proposed, you could just think about electrons and positrons as the same kind of particle moving in different time directions. This made the mathematics much simpler, much more elegant. And it led me to develop what we call Feynman diagrams, which is a way of drawing pictures that represent all the different ways particles can interact. In these diagrams, you can draw a positron as an electron with an arrow pointing backward in time. It's just a mathematical trick, but it's a very useful one. Let me show you what I mean with an example. Suppose you have an electron and it's cruising along through space. Then it interacts with light, with a photon. In the traditional way of thinking, that photon can create an electron-positron pair. The pair lives for a tiny moment, then the positron annihilates with your original electron. You end up with one electron going out, different from the one that came in. But in my way of thinking, what's really happening? The electron is traveling along, it interacts with the light, and it gets scattered backward in time. While it's going backward, we call it a positron. Then it interacts with the light again and gets scattered forward in time again. It's all the same electron, just changing direction in time. These two descriptions are completely equivalent mathematically. They give you exactly the same predictions for experiments, but thinking about it the second way makes the calculations much easier. And that's what physics is about, finding the simplest way to describe what's happening. Now, you might be wondering, is this really what's happening? Are positrons really electrons traveling backward in time? And here's what I have to tell you. Physics doesn't answer that question. Physics tells you how to calculate what will happen in an experiment. It gives you equations that predict the results you'll measure. Whether the positron is really going backward in time or whether it's really a separate particle, those are questions of interpretation. They're philosophical questions, not physics questions. What matters is that the mathematics works, and boy does it work. This way of thinking about antiparticles helped us develop quantum electrodynamics, the theory of how light and matter interact. It's the most precisely tested theory in all of physics. We can calculate things like the magnetic moment of the electron to 10 decimal places, and they match the experiments perfectly. But let's come back to Wheeler's crazy idea for a moment, because there's something beautiful about it, even if it's not literally true. Imagine that it was true. Imagine that every electron in your body, in the earth, in the stars, is the same electron, just at different points in its incredibly long journey back and forth through time. That would mean that every time you see an electron, you're seeing the same particle you saw before, just at a different point in its life. In a strange way, it would mean that this one electron has been everywhere, done everything. It's been in atoms, in molecules, in living beings, in stars. It's traveled across the entire universe, billions and billions of times, just taking different paths through the tangled knot of space-time. Now, we know this isn't really what's happening, but it's a beautiful thought experiment. It shows you how strange and wonderful the quantum world can be. It shows you that our ordinary intuitions about time and identity don't necessarily apply at the level of elementary particles. And here's something that's absolutely true. Whether or not you believe Wheeler's idea, you cannot tell electrons apart. There's no way to label an electron, to mark it somehow so you know which one it is. If I have two electrons and I swap them, there's no experiment you can do to tell that I've swapped them. They're fundamentally indistinguishable. This isn't just a practical limitation, it's a deep principle of quantum mechanics. The indistinguishability of identical particles affects how they behave. It's why electrons obey the Pauli exclusion principle, why you can't put two electrons in the same quantum state. It's fundamental to the structure of atoms, to chemistry, to everything. So in a funny way, asking which electron is this is not even a meaningful question. Electrons don't have individual identities. They're not like people, where each one has a unique history and characteristics. They're all exactly the same, interchangeable. Wheeler's idea takes this one step further and says, well, if they're all identical and interchangeable, maybe that's because they literally are all the same one. It's not true, but it's a provocative way to think about what identity means for elementary particles. Let me tell you what I learned from this whole episode with Wheeler. I learned that in physics, you should never be afraid to think crazy thoughts. The crazier the better, as long as you're willing to check them against reality. Most crazy ideas are wrong, but sometimes they lead you somewhere interesting. I didn't believe Wheeler's idea that there's only one electron in the universe, but thinking about it led me to see that positrons could be represented as electrons going backward in time, and that led to Feynman diagrams, and that led to quantum electrodynamics, and that eventually led to a Nobel Prize. So even wrong ideas can be valuable if they make you think in new ways. That's the essence of theoretical physics. You play with ideas, you follow them where they lead, you see what works and what doesn't. And here's the other thing I learned. Nature is under no obligation to make sense to you. The quantum world is strange. Particles don't have definite positions until you measure them. They can be in two places at once. They can tunnel through barriers. They can be entangled across vast distances. And yes, mathematically at least, antiparticles can be described as particles going backward in time. Your job as a physicist isn't to make nature conform to your intuitions. Your job is to figure out what nature is actually doing and then learn to be comfortable with it, even if it seems strange. Wheeler's one-electron universe idea taught me that. It's almost certainly not true, but it's the kind of crazy, beautiful idea that makes physics fun. It makes you question your assumptions. It makes you think about time and identity and what it means for something to exist. And most importantly, it reminds you that the universe is far stranger and more wonderful than anything we could have imagined. We're lucky to live in a universe where such ideas are even possible to think about, where the mathematics of physics allows us to explore these wild possibilities. So the next time someone tells you a crazy idea about physics, don't dismiss it immediately. Think about it, play with it, see where it leads. You might not end up believing it, but you might learn something wonderful along the way. That's what happened to me with Wheeler's telephone call in 1940. I didn't believe his idea, but I learned from it. And that, I think, is the best thing that can happen to a scientist. Not that every idea you hear is true, but that every idea makes you think, makes you see things differently.